Let's resume our discussion on sequences. We talked about the definition in precise terms, and we talked about limit and convergence, limit rules. We even talked about monotone sequence theorem, albeit briefly. Let's move on to examples. We have to deal with two types of examples here. One is when we have general terms, how to find a limit. Example 6 and 7 fall into that category. And the second type of the problem is when we have a recursively defined limit, how can you find out the limit? That's a little bit tougher, and we need monotone sequence theorem or things like those to be a little bit more precise there. Okay, let's move on to the simplest type. 1.6a, infinity over infinity type limit, and this is as simple as it can get. Both numerator and denominator are algebraic, and we can find out its growth order. The growth orders are 1/2 for both of them because they are both 1/2 power functions, basically. So we can expect the ratio of the highest order terms coefficient, and that's 1/1. But if you want to do it a little bit more precisely, here it is. Divide everything by highest order terms, and after that division, and then division, we're going to get this kind of simplification. And then we can simply plug in the numbers now because we don't have infinities anymore. We have 1 over 0 plus 1, that is equal to 1. If you're still dissatisfied with this, yes, I don't blame you. I was kind of like that too. In that case, you can do something like that. Follow everything to the utmost detail. So here, from here, split the limit by the limit rule, numerator and denominator. And then numerator, you can use the trivial limit rule, that's 1. Denominator, you can split them, again the limit rule. And then this is 1, and then that one can be rewritten as 1 over square root of n, just algebraic manipulation, and then slip the limit inside, generating square root of 0. Eventually you're going to get 1. So everything follows from the limit rule. But I do not think this is really necessary because all those limit rules are there to justify this kind of plugging in process. So it's okay not to follow all those. How about the next problem here? This is again infinity over infinity type limit, e to the nth power over n to the third power. The numerator has exponential order. The denominator has just third order. Excuse me. So it'll blow up to infinity. Exponential function has actually growth order of more or less infinity. You can take L'Hopital's rule 3 times like this. Exponential stays the same, and denominator eventually goes out. So we have infinity over 6. That's infinity. This problem is a little bit easier. I mean, a little bit more complicated. Excuse me, I said it backward. A little bit harder, but not too much. We have infinity minus infinity type limit. So that's a little bit harder, but if you can change it into fraction form and apply L'Hopital's rule, then you can do it. So how do you do that? Well, please note that this is a logarithmic function we are dealing with, so we can use log rule. Here, we can change this log minus log into log of fraction, and then just we have to this one is more challenging, square root minus something, or it can be applied to square root minus another square root. We have infinity minus infinity type limit. How do you deal with that? How do you change it into fraction? Early on we had log rule to help us. In this case, what do? As a matter of fact, this kind of problem showed up in Calculus 1. It's just that I didn't pay much attention to it. I intentionally shied away from that kind of problems because for Calculus 1 that was too hard, and also we were going to come back to this kind of thing in Calc 2. The typical technique here is to rationalize the numerator by multiplying the conjugate. So this expression can be written as, well, that over 1, and then rationalize the numerator by multiplying the conjugate. Square root plus 3n over square root plus 3n. And then you can expand the numerator a minus b times a plus b, so a squared minus b squared. Consequently, we can drop the square root, and then cancellation applies. We end up getting just n in numerator, and we're in business, because denominator has also growth order of just n. This 3n, okay, that's good. How about this 9n squared? But that's inside the square root, so 2 divided by 2 is 1. So both of them has growth order 1. Precise computation is like this. Now let's talk about a little bit more challenging problem, kind of like this one. Limit n goes to infinity, 1 plus 1 over n to the nth power, generating e. Okay, 1 to the infinity power form. How do you deal with those? Well, the very first thing I would prefer to do is to take the limit of this. An is 1 plus 1 over n to the nth power. So log of an will be log of 1 plus 1 over n. But then again, you can use log rule, right? N times log of 1 plus 1 over n. So n comes out. Now what do we have? We ended up with infinity times 0 type limit. N goes to infinity. Log of 1 plus 1 over n goes to log of 1 plus 0. Log of 1 is 0, so we end up with 0 times the infinity type limit. In Calc 1 level, most of the 0 times the infinity type limit ended up with 0, but not this time. We can change it into fraction form like this, and then apply L'Hopital's rule. And what do you end up getting? Well, you have to take the derivative of numerator and derivative of denominator and then work out. I'll leave the details to the students. If you do it right, you're supposed to get limit value 1, and consequently the log of this is log of an is approaching to 1, so an itself must approach to e. Another way to handle that is to convert it into, well, this kind of limit form. As a matter of fact, I just copied this limit problem from Calculus 1, so it looks a little bit more complicated. So, but basically it's following the same kind of method. How about the next one? 1.7b and 1.7c look more intimidating because, well, factorial. We haven't dealt with factorials at all in Calculus 1, and I don't remember dealing with factorials in pre-calc either. So out of nowhere, factorial is showing up, and that can intimidate students. I understand that. If you just remember what it is, then it's not going to be too much of a problem to guess that limit is going to be 0. The numerator is n times n minus 1 times n minus 2 times n minus 3 times all the way up to 1. The denominator is n to the nth power, so it's n times n times n times and so on. In short, we have something like this. Let's expand the font a little bit so that everybody can see these fractions a little bit better. So we have this fraction, so you can put those, decompose it into n over n, n minus 1 over n, n minus 2 over n, and so on. That goes all the way up to 1 over n. So early on, both numerator and denominators are big. The latter part, only denominator is big, numerator is not. So looks like denominator is going to be much bigger, so the limit will be 0. However, how do you justify that? Well, that's a bit tricky, and here it is. What I decided to do was to leave 1 over n at the very end and overestimate all the others by 1 because denominator is bigger. So this is very rough overestimation, but it works out anyway. In the end, what we got? This n factorial over n to the nth power is greater than or equal to 1, greater than or equal to 0, excuse me, and less than or equal to 1 over n, and both of them go down to 0. So applying the squeeze rule or sandwich rule, you can conclude that n factorial over n to the nth power also has a limit and then limit is the same value as before, 0. You can do something similar to part C, and that's a little bit more challenging, and I'm going to leave that to you guys. Now let's move on to the kind of examples that you'll have to use recursive relation. Actually, guessing the limit value is not too bad at all. Let's see, let's open it up. We are looking for something like this expression, but I don't know how much sense it makes. The key is this observation here. an approaches to a, and an plus 1 should also approach the same limit because both n and n plus 1 are headed toward infinity. So if I replace an plus 1 and an by a, the limit value, then we have a equation, and this is actually a quadratic equation. So we end up with this equation, and then we have two candidates, a equals to 0 or 2. Now the hard part, which is the limit. The limit has to be unique. We have a sequence, well-defined sequence, so if that sequence approaches to a unique number, that's a limit. If it gets pretty close to two different numbers, then it's just an oscillation. We don't have convergence. So what? Does it mean this is divergence? Actually, one way to see that is to do some numerical experiment, and then I just wrote a mathematical program to calculate this value, the limit, excuse me, not the limit value, but first 10th term. And as you can see, quickly these numbers are approaching to 1.99 something. So you can guess it's going to be 2, not 0. But that's just a guess. How do you actually justify that? Well, here it is. This is a recursive relationship, isn't it? an plus 1 equals the square root of 2 times an. If you replace an by one of the candidates 2, then what do you get? Well, an is always less than 2 because, actually no, not really. I'm jumping ahead a bit too much. With some mysterious assumption, an is less than or equal to 2. Once you make that assumption, then it works out. An is less than 2, so everything is less than square root of 4, so even an plus 1 is less than 2. This kind of thing is called inductive argument. Starting from a0, which is 1, and that's less than 2. So a2, by this argument, is less than 2 because just a0 is less than 2, so replace a0 by 2, then a2 is going to be less than 2. Because a2 is less than 2, plug it in again, then you're going to get a3 is less than 2. a3, excuse me, I have to highlight here. a2 will go over here, that's going to be replaced by 2. So a3 will be less than 2 and goes on forever. So from this inequality and then the very first term, we can conclude that this is a bounded sequence. So all the an's, a1, a2, a3, and so on, those are all less than or equal to 2, bounded sequence. Now, next observation. If an is all less than or equal to 2, which we just proved actually, let's replace 2 by an. So we made this smaller. And then if you have an times an inside square root, what do you get? It's just an. So what do you have? An plus 1 is greater than or equal to an. And that also works kind of inductively. Plug in n equal to 0, and then a0 is less than or equal to a1. Plug in the same thing to a1, then a1 is less than or equal to a2, and so on. So what do we have? We have a increasing sequence that is bounded above, and we are beginning from 1, so we have to increase. It's not going to be 0. We have to go all the way up to 2. So you have to use, in order to be really precise, you have to use that bounded convergence theorem. But even if you do not write all those things down, if you somehow conclude a equals to 2 by some numerical experiment or whatever, then you'll get full credit. The other problems are kind of similar too.